I'm going to talk about continual learning. And maybe it's good to start by saying that my experience and also this talk, it's mostly on continual learning from the perspective of deep learning or conventional deep learning. But that doesn't mean that it's not relevant for neuromorphic computing. And also continual learning is something that conventional deep learning really struggles with. So maybe this could be an area where neuromorphic computing might have an edge. Okay, so here's an overview of my talk. So as many of you might not be familiar with continual learning, I'll start with an extended introduction in which I'll cover what is continual learning, why is it important, and why is it so challenging. And then in the main part, I'll first discuss what the current approach to continual learning is, and then I point out a fundamental limitation to this approach, and I end by proposing a new direction for continual learning. Okay, but so first, what is continual learning? So with standard machine learning, when training a model, the typical assumption is that all the data on which the model is trained are available at the same time. But with continual learning, this is not the case, and there are two key differences. So first, the training data arrive incrementally in a number of sequential steps. And second, the distribution of the training data changes over time. And a useful way to think about this is in terms of tasks, that a model must first learn task A, then task B, then task C, etc. And importantly, at the end of training, we then want a model to be good at all tasks it has seen. And so I would argue that such continual learning is a key aspect of intelligence. Our brain is an example of an excellent continual learner, but unfortunately, current AI algorithms are not good at continual learning. And this is a problem. But why is it a problem? Why is it important for AI algorithms to be good at continual learning? So let's consider an example. So say we want to build a self-driving car. So to do so, we collect a lot of training data, and on those we train a big, powerful model. And then we deploy it. And say it goes well for a while, but then the car crashes because, as it turns out, our model does not recognize white trucks. So what do? We collect more data of white trucks. And now it would be nice to continue training our current model, which is otherwise functioning fine, on this new data to improve the model's capability of recognizing white trucks. But this is generally not what is currently done. Instead, common practice in industry in this situation is to fully retrain the model on the entire data set. And so currently, this is what gives the best performance, but it is very resource intensive. And so now the goal of continual learning is to try to improve this process, to enable continual training, to be able to add capabilities to existing models in much more efficient manners. And in the last 10 years or so, such continual learning has become a very popular topic, especially in deep learning. But yet, practical applications of continual learning with deep neural networks remain rare. And so continual learning is, I would say, still largely an unsolved problem. Okay, so why is continual learning so difficult? And especially why it's so difficult for deep neural networks? And an important reason for this is catastrophic forgetting. And let me explain this phenomenon with a schematic. So here we have a neural network that must learn two tasks, the orange one and the blue one, while being trained on them one after the other. And so when the network is trained on the first task, as you can see, and as expected, the performance of the network on this task steadily improves. But then when the network is trained on the second task, the network's performance on the new task steadily increases, but the performance on the first task drops rapidly. So when the network is trained on a new task, it forgets the previously learned task, and it tends to do so in a catastrophic manner. It tends to do so very fast. And importantly, this forgetting is not due to the capacity of the network or capacity limits, because if the same network would be trained on both tasks at the same time, it would be able to learn both. So the forgetting is due to the temporal order of the learning, and that's important. Okay, but catastrophic forgetting is an important challenge for continual learning, but it's not the only one. So in addition to avoiding forgetting, successful continual learning methods should also be able to rapidly adapt to new situations, to exploit similarity between tasks, to operate in task-agnostic manner, to be tolerant to noise, and to be sustainable and efficient with resources. So continual learning is a complex problem. And then to make things even a bit more complex, depending on how the data from which is being learned changes over time, so whether there are new tasks, new domains, or new data, or new classes, we can distinguish 3 different types of continual learning with each their own challenges as well. Okay, so that was the introduction, and to very briefly summarize, continual learning is the problem of incrementally learning from a non-stationary stream of data. Continual learning is important because it can enable updating or improving trained models in much more efficient manners. And catastrophic forgetting is a main challenge, but not the only one. And so far in this introduction, I have described or characterized the problem of continual learning. And now in the main part of this talk, I will talk about how to address this problem. And I will do so first by explaining what the current approach to continual learning is. And I'm going to do that using this simple example. So this example, I think it gets to the core of the continual learning problem. For example, because it's actually relevant for all the 3 types of continual learning that I mentioned before. So here we have a model F and parameters W that we want to optimize for 2 tasks that are encountered one after the other. And well, to come back to the example that I used before, task 1 can be the initial data set for training self-driving cars, and task 2 can be the additional data for recognizing white trucks. Okay, so first, what do? We train the model on the first task. And then if we continue to train on the second task in the standard way, so that means to use gradient descent to optimize the loss on the new data, so the loss on the new task, on the second task. Then what we get is catastrophic forgetting. So we get a model that is good for the second task, but no longer for the first one. So instead, to prevent this forgetting, what people do in continual learning, the current approach to continual learning is to make changes to the loss function that is optimized when training on the new task. And in particular, rather than using gradient descent to optimize only the loss on the new task, this current approach to continual learning is to use gradient descent to instead optimize an approximation to the joint loss over all tasks so far. So examples of this approach are, for example, replay, parameter regularization, and functional regularization. And the details of these methods are not really important now. I just need to point out that all of these methods do, all these types of methods, they add extra terms to the loss function. And these extra terms, they can be interpreted as approximations to the loss on the all tasks. And so this is, I would say, a sensible approach to continual learning. And in the last couple of years, it indeed has had some success in improving the continual learning capabilities of deep neural networks. But my question is it enough? And my answer to this question is no, it's not enough. So my claim is that more than this is needed. So I claim that although this current approach to continual learning, so changing the loss function that is optimized, should indeed be one component to the solution of the continual learning problem, but that by itself it's insufficient. And maybe it's good to point out that actually there are, like, besides replay, parameter regularization, and functional regularization, there are already existing approaches for continual learning. For example, context-specific components or using a template-based classification. But although these approaches are important and very useful in practice, they are not what I'm looking for here. And the reason is that these approaches, they do not address what I would call the core continual learning problem. They they are not approaches for optimizing a shared set of parameters in a continual manner. So rather, they are approaches for introducing specialization into a network. Okay, so back to this claim of mine that the current approach to continual learning is insufficient for fully addressing this core continual learning problem. And to convince you that this is the case, I'm going to discuss what I think is a very fascinating phenomenon that my colleagues and I described recently, and that we called the stability gap. Okay. So let me explain. So here we have I would say standard class incremental learning experiment, split mini ImageNet in this case, where a deep neural network must incrementally learn a sequence of tasks. And on the y-axis of this graph, the average test accuracy on the first task is plotted, while the network is incrementally trained on the first 5 tasks of this task sequence. And so already plotted is the improvement in the task 1 accuracy when the network is being trained on task 1. And the red diamond is the performance on task 1 after finishing training on task 1. And so now what we're going to do is we're going to look at what happens to the accuracy on task 1. So that's important, while the network continues to be trained on the other tasks. And when we continue to train the network on the other task, we're going to use experience replay. So one of these current approaches to continual learning. And experience replay means that when we train on the later tasks, we will mix in or replay some stored examples from the first task. So essentially, we keep retraining on the first task. So what will happen? So considering that replay is considered sort of a very effective continual learning method, presumably we expect that it will prevent forgetting or minimize forgetting. And if we would only evaluate the performance of the model at the end of training each task, as is sort of the default approach to evaluation in continual learning, then as you can see, well, forgetting is not fully prevented, but the forgetting is quite gradual. It's the performance of this model is quite good. So replay seems reasonably successful in reducing forgetting. But if now, rather than evaluating only at the end of training on each task, we instead evaluate after each training iteration, then we get a completely different picture. Because then, quite strikingly, I think it turns out that there is very substantial forgetting of task 1, except that this forgetting is temporary and it's followed by a phase of performance recovery. And this performance recovery is spontaneous in the sense that we don't change anything. So I said, okay, we use replay, but this replay is used all the time. This replay is already used at the beginning of training the new task. We don't change anything towards the end of training on the task. So this shows, at least to my initial surprise, that at least part of replay's contribution to continual learning is not through preventing forgetting of past tasks, but rather through enabling the relearning of those past tasks. And we found that this phenomenon of temporary forgetting when starting to learn a new task is consistently found in a wide variety of continual learning experiments, as shown here on a more class incremental learning experience with using replay, but also in task and domain incremental learning and with regularization-based methods. Okay. So this stability gap is very consistent, but you might still ask, okay, why should we care? Because if the forgetting is only temporary and it automatically recovers, what's the problem? So firstly, I would say, okay, if you want to apply your continual learning algorithm to safety critical applications where the worst case performance of your algorithm is important, then this is obviously something that you should be aware of and that you should care about. But in some sense, more importantly, I think, also if you don't care about this online performance, I think the stability gap is undesirable. Because essentially, when training on the second task, the first task is for a large part relearned. And so to me, this is indicative of suboptimal optimization, or at least a suboptimal optimization trajectory. Because when learning a new task, why should the network first forget previous tasks and then later relearn them? Should it not be a lot more efficient to simply prevent forgetting of the first task in the first place? And then also, as kind of more of a side note, I think this temporary forgetting in these neural networks is just intriguing in itself. It's scientifically interesting. It raises the question whether we as humans might also suffer from such a stability gap. That is, when we learn something new, do we, while learning this new task, temporarily forget previously learned tasks? And so together with some colleagues from cognitive science, I'm currently setting up some experiments to test whether we can indeed find something like the stability gap in humans as well. But that's more to the side. So I made an argument that the stability gap is undesirable, and let's ask, okay, could we avoid it in deep neural networks? And in particular, let's begin by asking, okay, could we avoid the stability gap using the current approach to continual learning? Because maybe in the examples that I showed, I simply did not use enough replay, or the regularization that I used was simply not strong enough. So if we improve replay or improve regularization, could we maybe get rid of the stability gap? So to test whether this is possible, what I'm going to do is to simulate the sort of, I'm going to simulate the best case scenario for these replay and regularization based approaches. I'm going to simulate the best case scenario for the current approach to continual learning. So I'm going to use perfect replay or perfect regularization. That is, rather than approximating the joint loss, as these methods do, I'm always going to just use the actual joint loss. So in other words, I'm going to do incremental joint training. And this incremental joint training, it's kind of the upper bound or the best case scenario for the current approach to continual learning. It's the best we can hope for if the continual learning field would continue on this current path. Okay, so if we use this incremental joint training, is there still a stability gap? And quite strikingly, yes, there still is a stability gap. So even the best case scenario for the current approach to continual learning, even using perfect replay, like full replay or perfect regularization, we still have the stability gap, and quite a substantial one as well. So it looks like we need something else. We need to do something else. But first, maybe we should also face the possibility that actually there's nothing we can do, that this stability gap is simply unavoidable. You can think, okay, maybe the solution to the first task is in some kind of local minimum, and to get to a better solution, to get to the joint solution, we have to get out of this local minimum by temporarily forgetting a bit. So that's a possibility, but yeah, let's see whether that is the case or not. And interestingly, or luckily, at least for the examples that I showed you, this is actually not the case. It is actually possible to avoid the stability gap, and I'm going to show you. So after training task one on in this paradigm, let's call the parameters of the model that we find W old. And then after training on task two, so again, while doing replay on task one, let's call the model parameters WCL. And so now, as this graph shows, when we went from W old to WCL, when we used gradient-based optimization, the trajectory that was taken, along this trajectory, there was substantial forgetting of task one. And now the question is, okay, is there, or could there be another trajectory from W alt to WCL along which there is not such forgetting? And as it turns out, there indeed is a trajectory, and there is even a linear trajectory. If we simply take sort of a linear interpolation between W alt and WCL, and we evaluate the performance along this linear trajectory, there is no dip in the performance on task 1. So there's no stability gap. So this shows that there actually is a trajectory. It would have been possible to go from W alt to WCL without forgetting the previous task. It's just that gradient descent-based optimization did not find this path, and it took a different path. Yeah, as shown here. Okay, so where does this leave us? That's to the end of my talk, and with my proposal for what should continual learning do instead, or what should continual learning do additionally? And so I think what I showed you, this stability gap, I think it shows that the current approach to continual learning is not enough, that more is needed. So in order to overcome the stability gap, continual learning needs to focus not only on what to optimize, on which loss function to optimize, but also on how to optimize, on how to do optimization of the objective. And I would argue that this proposal also makes sense considering that the standard gradient descent-based optimization routines for deep learning, that they have all been developed for the stationary setting. They've been developed and tested in the stationary setting. And there's no guarantees for these methods in the continual setting, but yet they're widely used in this setting. And indeed, the experiments I showed you, they demonstrate important shortcomings of these standard optimization methods in this continual setting. And one explanation for this can be that there is actually a fundamental difference between optimization in the stationary setting versus optimization in the continual setting. And that is that in the stationary setting, optimization always starts from a random initialization. But in the continual setting, the starting point is not random. The starting point is a partial solution. And it makes sense that when you start from a partial solution, you might want to do optimization differently than when you start from a random solution. You might want to have some kind of optimization routine that is a bit more, a bit less greedy, that's more respective of what you already know. And so yeah, so that's my proposal, that the field of continual learning should really focus on this optimization and should think about how can we develop better ways of optimizing that are specific for the continual setting. And well, how to do this? I'm afraid I don't have really an answer to that yet, but I think it's an exciting open question, and I think it's necessary. It's an important question that I think is necessary to address in order to pave the road towards developing continual learning techniques that are suitable for real world applications. And also, I want to end with that perhaps this could be an opportunity for techniques from neuromorphic computing that could be applied here, and I'd be interested to discuss any ideas in that regard. Okay, thanks.